So theorem. This theorem, I'm not going to write it in the most general form, but like it's the one that will be most useful to us here. It'll be convenient to write it down this way. Um, so um, if f from u removed, u with z not removed to c is differentiable on a a punctured disk. So that's a it's a ball, right? A punctured disk is a ball centered around Z naught, but with the center removed. All right. So the center is removed. So if our function is differentiable except at that singularity, then it has a Laurent series expansion. Um, Centered around Z naught. So what is a Laurent series expansion? Um, it's simply a generalization of a Taylor series, but where we can have negative powers of Z minus Z naught as well. So f of Z looks like, it's a doubly infinite series with potentially some negative powers of Z there. Okay. Okay. So, if your function is differentiable on a ball around Z naught, then it has a Taylor series centered at Z naught. So only, starting A naught and so on, only positive, non-negative powers of Z minus Z naught. But if it's differentiable on a punctured disk, then at least it has a Laurent series, right? So it may have some negative terms. So it kind of makes sense. Like, I mean, if I plug in Z naught, obviously I get something that's kind of not defined. But I can plug in anything different from Z naught. Okay, so okay, now for a definition. Um, it's a three-way definition. One, two, three. If um if the lowest power of Z minus Z naught in the Laurent expansion is minus n in Z, right? I.e., f of Z starts a minus Z, Z minus Z naught to the minus n, and so on. Then we say f has a pole. I have not enough space. Has a pole of order n at Z naught. Okay, so if this Laurent expansion in fact kind of isn't isn't infinite in that direction, right? It stops somewhere at some power of z minus at some z minus z naught to the minus n, then we say f has a pole of order n. Um, if on the other hand the minimum, you know, n, or if if the set n of kind of indices such that a n is not zero, it is not bounded below, right? So actually this expansion goes on forever. Then we say f has an essential singularity at z naught. And three, if in fact a to the negative n is equal to 0 for n greater or equal to 1. So in fact actually there isn't any negative powers. Then we say f has a removable singularity at z naught. Removable because if in fact f of z has a Taylor series expression in the punctured disk, then we could redefine f. We could extend the definition of f to z naught by simply defining it with this formula, with the Taylor series formula, right? So in that sense, it's removable. Okay. So more blue writing. And now another theorem. If, let's call it h of z, is holomorphic at z naught and has a 0 of order n at z naught, then 1 over, you know, the function f of z equals 1 over h of z. Guess what? It has a pole of order n at z naught. And you know, while we're here, why don't we say kind of a bit more that if h of z and g of z are holomorphic at z naught, and h of z, mm, oh, so there's a lot, there's a few different cases. Holomorphic at z naught, then a few things. If let's say if H and G have zeros, let's call it like if H has a zero of order n at Z naught, and G has a zero of order m, then H Z G Z has a zero of order n plus m at Z naught, right? So if H has zero of order n, G has zero of order m, then the product, the orders add up, right? And for that, think kind of Z minus Z naught to the n times Z minus Z naught to the m equals Z minus Z naught to the n plus m, right? That's essentially, kind of the reason behind it, yeah, with a lot of detail removed. If G has a pole of order um, m, where m, let's say it's less than n, then um, G H Z G Z, the product has a zero still of order um, n minus m. Again, think now, a zero of order n times a pole of order m, kind of as 1 over z minus z naught to the m, is equal to z minus z naught to the n minus m, right? But because n is bigger than m, that gives us a positive power. So that's a zero of order n minus m, not a singularity. If on the other hand, G has a pole of order m greater or equal, so it's actually strictly greater than n, then HZGZ, it has now not a zero, but it has a pole of order, let's see, m minus n, right? Again, what you want to think about is something like z minus z naught to the n times 1 over z minus z naught to the m. Well, now m is bigger than n, so we'll get a positive power in the denominator, giving us a singularity, a pole of order m minus n. And if G has a pole of order m equals to n, then guess what? The product has a removable singularity. You can think of a similar thing there, right? And finally, I guess, what's the last case if H has a zero of order uh, No, sorry, a pole of order M at Z naught, and G has a pole of order M at Z naught, then the product HZGZ has a pole of order N plus M. So, I mean, this is all written in such a complicated way, but it's actually so simple. I mean, if you if you kind of think about like a pole of order n corresponds to sort of, negative n, like a negative integer, right? While a zero of order m, say, or yeah, of order m as simply the a positive, you kind of associate that with a positive integer m, right? Then a kind of a, z, a zero order m times zero order n, that's just m plus n, positive, that corresponds to m plus n, so that corresponds to a zero of order m plus n, while a sort of a pole, if you have a pole, if you mix a pole of order m with a zero of order n, well, that gives you n minus m, right? The zero is kind of the positive n, whole order m corresponds to minus m. You add them up, that's n minus m. And that's, well, either a zero if n is bigger than m, and so this turns out to be positive, or a pole if m is bigger than n, or removable if they're balanced, if m equals n, and then if you have a pole times a pole, then they add up.